we have been discussing testing of sequential circuits. See, most of the circuits that we come across in practice are sequential in nature, right. For example, microprocessors, okay. Microprocessors, microcontrollers, digital signal processors, communication controllers, protocol controllers, they are all sequential circuits, right. So, they all have the same, we can represent them in the way I explained yesterday. So, they have primary inputs and primary outputs, and there is a state register, right. I have written it as a register. You can imagine the register as a number of flip flops, right, and this is the previous state and this is the next state, right. So, the there is a reset signal usually provided in order to set the initial state. So, we can start by resetting the machine, this finite state machine, okay, or FSM, and then there is a clock which is provided to synchronize the changing of state. See, if you remember, there may be number of flip flops, okay. Imagine that there are 3 flip flops, right. So, it might look like this. So, there is D0 coming in and Q0, D1, Q1, D2, Q2, right. So, there may be number of such flip flops, right, which are getting okay, and this may be your combinational logic. These are your primary inputs, primary outputs, right. So, what might happen is when the primary inputs are changed, there are the outputs here, the state outputs, the next state outputs. There is some delay, right. I mean, there are gates in the combination logic and they have delays. So, there is no guarantee that these 3 signals will be ready at the same time. It is possible that one of them takes a little longer than the others. So, they will all respond to the changes in the primary input, and the next state, okay, suppose the initial state was 101, okay, the flip flops contained the value 101, and let us say the next state is 010, okay, it goes from state 101 to 010. So, you see excuse me. So, Q naught has to change from 1 to 0, Q1 has to change from 0 to 1, and Q2 has to change from 1 to 0. And these may not happen at the same time, there may be some small delays, maybe Q1 takes the longest, right. So, it is possible that this changes the fastest, this has remained 0 and it has not yet changed, and this has remained the same. So, for a brief period the state 0 0 0 will appear, then maybe this guy changes to 0, and this has already changed to 0. Then finally this will change to 1. Okay. So, briefly there is a state 0 0 0 that has appeared, right. It can also happen that from one, the first one changes the fastest, second one has still not changed, the third one also has still not changed. So, briefly the state 0 0 1 will appear, then maybe this guy changes to 0. Okay, finally it has made the change. So, the state 0 0 0 will appear, and finally this changes to 1 and the correct state appears 0 1 0. So, there may be a number of intermediate states that can come up. So, we need to synchronize, we need to be able to tell this machine that when the next state is ready. See the which is the next state. If this is the previous state, this is not the next state, this is not the next state, this is the correct next state. So, if that has to be communicated to the machine, we need a clock signal, right. There is a clock signal which is common to all the circuits, right. So, this is a clock. So, the idea is that even though Q naught may change, and so once upon a time they used to design what are called as asynchronous circuits, right. So, D naught will be directly connected to Q naught, D 1 will be directly connected to Q 2 and so on. So, this is an asynchronous system. Okay. So, here the difficulty is that this problem may occur, right. So, what we do is we insert these flip flops here, right, and we wait for the clock to go from 0 to 1. So, that is the clock is a synchronizing signal. When the clock goes from 0 to 1, that is when all the D's are transferred to Q's. So, D 0 will get copied to Q naught, D 1 will get copied to Q 1 and D 2 will get copied to Q 2. So, that is what a synchronous sequential circuit is. So, synchronous, okay. So, it requires a clock, all right. So, like I was telling you, all these machines that we come across, all the circuits that we come across, microprocessors, microcontrollers, DSPs, all of them are synchronous sequential circuits, right. So, when you are designing a digital circuit, okay, then usually it is nowadays common to use a high level language, okay, a hardware description language. A hardware description language may be Verilog, VHDL and so on. Okay. And these are designed usually at a higher level of abstraction, right. We assume that we have building blocks like registers, ALUs, multipliers, multiplexers, buses. So, these are the kind of building blocks that we use, and such a design is called as register transfer level design. Okay, so, RTL design. And then usually there is a synthesis that is required, okay, to get what is called as gate level design. But before we go to synthesis, right, we will have to check whether the design that we have done is it's the correct design. What if there are bugs in the RTL? Okay, there could be bugs. Okay, when we write the description in an HDL, see this HDL looks a lot like C language. Okay, so Verilog, for example, has a lot of similarity to C language. And when we are writing the HDL, we may make a lot of errors, right? Not syntax errors. Okay, these are functional bugs that we have introduced. Okay. A very simple trivial example could be, we wanted to assign variable x to let us say y. Let me see, the variable names are usually chosen to be more meaningful, right. So, we do not usually use x and y. Okay. We may use things like maybe we can say image, memory, RAM, I. Okay. So, we may be assigning this to some maybe pixel or something like this. Okay. And it is possible that somebody had another variable called image, memory, RAM 2 or something like that. See, this is very likely. Okay. So, people may have designed so by mistake we may have copied we intended to write 2 here, but we forgot. Okay, we made a mistake, and both of them are valid. Okay, so, we are copying the wrong variable. This is not a syntax error. Okay, this is not a syntax error. Okay. This is a functional bug. Okay, we copied the wrong variable. Okay. So, things like this may exist in our RTL code, and we have to make sure that we do not have these bugs. Okay. So, how do we do that? So, we go through what is called as verification. Okay. So, we perform what is called as verification. So, we write test benches. Okay. So, test benches are written to check whether the RTL performs the way it is supposed to, right. So, the purpose of verification is it compares the implementation with the spec. or the specification, and if they are different, we will find the bug. Okay, we have found a bug if there is some test bench in which the specification and the verification, I am sorry, the specification and the implementation are producing different results. Okay. So, after a extensive amount of verification, we may realize that the bugs have all been removed, right. When we find a bug, we need to go and fix it, right. So, a stage will come when all the bugs that we are aware of, right, have been removed, right. We are fairly confident that we have gone and implemented things correctly, right. We can never be 100% sure that all the bugs have been removed, right. But we may reach a high level of confidence, we may achieve a high level of confidence in saying that I believe that there are no bugs left in the verification, I am sorry, in the RTL design. Okay. It is after that we go through synthesis, right. So, verification, and if there are bugs, we go back. Okay. And when there are no bugs, we are ready to synthesize. That is how it works, right. Now, the point is, now let us say I have my microprocessor, which is in now silicon. Okay. We have managed to go from the RTL design to gate level design. We have also done what is called as physical design, and we have finally got the silicon back. We have manufactured it and we have come back, right. The question is, how do we test this guy? Okay. So, please understand that there is a difference between verification and testing, right. Verification is what we do when we are still in the early stages of design. We do not have any silicon. Okay. We have a Verilog file or a VHDL file which describes the hardware that we intend to sort of manufacture, and we have written test benches and we are trying to remove the functional bugs. Whereas testing means we have already manufactured, okay, and we may have a number of these. See, it is not going to be manufactured in one. Okay. So, there may be millions of these. Verification is only done on one model. Okay. We do not have millions of models, we only have one VHDL file or one Verilog file. And so, now when we want to test, can we use the same verification tests that we developed? Okay. So, in verification also we have to apply some inputs and we have to observe the outputs, right. So, that is what a test bench is. Now, the question is, can we apply the same functional tests? Okay. So, those are called functional tests. See, for example, in a microprocessor, if you read the data sheet, it may say that when you activate the reset signal to the microprocessor, the program counter goes to zeros, and as a result the address bus will become all zeros. Okay. That is a functionality of the microprocessor. Okay. So, we can apply the reset and see whether that is really happening. Okay. And then we can see whether it is able to fetch instructions correctly. Okay. then we can try to see whether it executes the simple no op instruction. Okay. No op means no operation. So, we can try to see whether the microprocessor executes the no op instruction. That means the program counter keeps incrementing correctly. Okay. So, these are called functional tests, okay. And the microprocessor's functionality is fairly complex, right. It usually has a number of different instructions, right, move, add, subtract, multiply. Okay. So, if you look at the ARM microprocessor for example, there are many instructions, okay, logical instructions, arithmetic instructions, branch instructions, data movement instructions, right. Now, can we really go and write small functional tests to test each one of these functionalities? Okay. Well, that looks appealing, right. It looks appealing that we should do something of that nature, right. The point is that is very impractical. Okay. The number of functional tests that we may have to perform on silicon to sort of quote unquote test the microprocessor, okay, will be very large. Okay. So, I have not mentioned this before, right, but I thought that may be a good thing to point out at this stage, right.